Everybody, welcome to week 7. This week we're going to be talking about basic key exchanges. Some of the objectives are going to be the introduction to key exchanges, symmetric versus asymmetric key exchanges, and the Diffie-Hellman key exchange, or the DHKE. So first, let's get right into it. So let's talk about the basic key exchanges. So the definition of the basic key exchanges is that key exchanges is a method used in cryptography that allows two or more parties to exchange keys that are used to encrypt and decrypt messages. This process ensures that each party has the necessary tools to decode messages received from others. Some important things about key exchange is that the key exchange process is crucially important in establishing secure communication channels. It ensures that transmitted data remains confidential and cannot be accessed or manipulated by unauthorized individuals or parties. So the process of key exchanges is that in a typical key exchange process, each party generates a pair of keys, one public and one private. The public keys the public keys are then exchanged. Each party uses its own private key in conjunction with others' public key to compute a shared secret key. This secret can then be used to encrypt and decrypt messages. So then let's actually get more into about symmetric and asymmetric key exchanges. So symmetric key exchange involves using the same key for both the encryption and decryption of a message. This means that a key must be securely shared, which can present challenges in insecure networks. Asymmetric key exchanges, on the other hand, utilizes a pair of keys, a public key for encryption and a private key for decryption. This approach allows for more secure communication without the need of a secure initial key exchange. So, security within the key exchange. The security in key exchange is based on certain computational hardness assumptions. These assumptions make it computationally feasible to calculate the shared secret key using the private key and the other party's public key, but extremely difficult to do so without the private key. So let's talk more about the key exchanges algorithm. So there are various key exchange algorithms available that are designed to facilitate this process. Some of the most common include the Diffie-Hellman key exchange, or the DHKE, the Diffie-Hellman, the DHE, or the ecliptic curve Diffie-Hellman, which is the ECDH. Each has their own advantages and are used in different scenarios. So some real world applications of the key exchange is that the key exchange protocol plays a crucial role in many real world applications. They form the basis of secure web browsing through the HTTPS and secure remote access through the VPNs, and then secure instant messaging applications, email encryptions, and much more. So, as I mentioned in previous lectures, when we think about websites that we join, sometimes you'll see the HTTP and sometimes you'll see it HTTPS. The S just reassures that the website is more secure. So now let's more so go into the how symmetric versus asymmetric key exchanges work. So we'll talk about each of them individually, and then we'll talk about them collectively. So first one, we're going to be talking about the symmetric key exchange. So symmetric key exchange, as mentioned, also known as a secret key exchange, involves using the same key for both encryption and decryption processes. For instance, if Alice wants to send a certain message to Bob, both Alice and Bob will need to have the same key. An example of symmetric key exchange is the Advanced Encryption Standards, or the AES, which is widely used in data encryption. The main advantage of the symmetric key exchange that it is more efficient. The encryption and decryption process are much more faster and require less computational resources compared to asymmetric key exchanges. However, the main challenges with symmetric key exchanges lies in the security distribution of the key itself. Alice and Bob must have a safe way to share the secret key without any third party interrupting them. So now let's talk about asymmetric key exchanges, also known as a public key exchange, using a pair of keys for the encryption and a decryption process. One key is a public and the one key is public and can be freely distributed, while the other key is a private key and it must be kept confidential. For this instant, if Alice wants to send a secure message to Bob, Alice can encrypt the message using Bob's public key. When and then when Bob receives the message, he can then decrypt it using his private key. Um, the beauty of this process of asymmetric key exchanges is that it navigates it negates the need for Alice and Bob to share a secret key in advance. Examples of asymmetric key exchanges includes the RSA and the ECC, as we discussed before, both of which are widely used in secure communications. Although asymmetric key exchanges require much more computational resources and is slower compared to symmetric key exchanges, it provides a more it provides a more practical solution for secure communication over open networks. So now let's do a comparison. How do they compare? So when comparing symmetric and asymmetric key exchanges, it's important to consider a specific requirement of the actual situation. If computational resources are limited and a secure channel for key exchange exists, symmetric key exchange may be the best choice. On the other hand, if secure communication needs to be established over an open network and there is no secure channel for each key exchange, asymmetric key exchange is likely to be the best and more suitable option. As a rule of thumb, asymmetric key exchanges, while slower and more resource intensive, provides a more secure and much more feasible solution for secure communication in the majority of real world applications. So now let's actually do a quiz question. So, which of the following is a major drawback of asymmetric key exchanges? Is it is it A, it is less secure than asymmetric key exchanges? Is it B, it requires more computational resources than asymmetric key exchanges? C, it struggles with the secure distribution of keys? Or D, it cannot be used for encryption or decryption? Major drawback of symmetric key exchanges is the difficulty in securely distributing keys. So the answer would be C. Well, let me actually do this, circle it over here for anybody watching. So while symmetric key exchanges is generally more efficient than asymmetric, securely sharing the key between sender and receiver is a significant challenge. The key must be exchanged over a secure channel to prevent interception, which is not likely a practical or possible in many real-world applications. Cool. So let's go on to the next. Perfect. We have another question here. So, in the context of asymmetric key exchanges, what ensures that the encryption remains secure even if the public key is known? Is it A, the computational complexity of the encryption algorithm? Is it B, the private key which remains confidential? C, the security of a key exchange process? Or D, the size of the key used in the encryption process? So, in asymmetric key exchanges, the encryption remains secure because the private key, which is used for decryption, remains confidential. So, that would be B. Even if an attacker knows the public key and intercepts the encrypted message, they can't decrypt the message without the corresponding public key. The corresponding private key. This allows for secure communication over an open network without the need of a secure initial exchange of secret keys. Okay, next one. So for this one is, why might you choose asymmetric key exchange over symmetric key exchanges when secure communication needs to be established over an open network? Is it A, asymmetric key exchange is faster and less computationally intensive? B, asymmetric key exchanges eliminates the need for secure key distribution? C, asymmetric key exchanges uses the same key for encryption and decryption? Or is it D, asymmetric key exchanges is less secure than symmetric key exchanges. So asymmetric key exchange is a better choice when secure communication needs to be established over an open network because it eliminates the need for secure key distribution, which is letter B. So while symmetric key exchanges requires a secure method for the sender and the receiver to share the same key, asymmetric key exchanges uses a pair of keys, a public and a private. A public key which can be openly shared and used for encryption, and a private key which remains confidential and is used for decryption. This makes a more practical solution for secure communication over an open network. Perfect. Now let's go on to the next one. Cool. Let's more talk about the Diffie-Hellman key exchange, or the DHKE. So the DHKE is a cryptographic protocol that allows two parties to establish a shared secret over an insecure and not a secret channel. The introduction by the Wolffield Diffie and the Martin Hellman in 1976, it marked at the beginning of the public key in cryptography. The shared secret can then be used for the symmetric encryption of a sequential communication. This method underpins the security of many modern communication systems, from secure emails to online banking. So, in the Diffie-Hellman key exchange, each party first generates a public-private key pair. The public keys are openly exchanged, while the private keys remain secret. So always remember, private keys are private, public keys are public. The parties then use their private keys. They use their private key and the other party's public key to independently create a shared secret. The beauty of this method is that even though the public key and the shared secret communication methods are open knowledge, depriving the secret depriving the shared secret from this information is computationally unfeasible without one of the private keys. So basically, if you have a public key and you have a message, you can't really do anything with it unless you have a private key. Perfect. Let's get to the next one. So, modular arithmetic, one of my favorite things. We actually talked about it previously in the past lectures. I believe it was like lecture number 3 or 4, but we talked about modular arithmetic, and I remember I talked a little bit about it because I knew that there are certain areas that we're going to use it and certain areas that we're not going to. So in the beginning, I gave you a more of an in-depth version of it and gave you some problems revolving around it. But for modular arithmetic, also known as the clock arithmetic, is a fundamental component of the DHKE. It involves integrals in a system where numbers wrap around, which is the hence of the clock, because a clock, every time it passes 12, it goes to 1. Upon reaching a certain value known as the modules. For an example, if we use 12 as a module, then 13 becomes 1, 14 becomes 2, and so on. Just like the hour on the clock, in the context of DHKE, modular arithmetic established the computations that creates a shared secret from a private key and a partner's public key. Now we're going to talk about discrete logarithm problem. So the security of the DHKE relies on the difficulty of the discrete logarithm problem. So this problem states that a given a and b and p, and an equation that b equals a to the n mod p, it's easy to compute b if a and n and p are known. However, finding n if a, b, and p are known is computationally difficult, especially when p is a large prime number. This one-wave function forms the basis of security in the DHKE because even if a eavesdropper intercepts the public key and knows P, they can't feasibly computate, can feasibly um, compute the shared secret without one of the private keys. Now we talk about the DHKE's process. So the DHKE process begins with both parties independently selecting a private key and computing a corresponding public key. The public keys are then exchanged over a insecure channel. Upon receiving the other party's public key, each party then calculates the shared secret using their own private key and the received public key. Due to the properties of the mathematical operation used, both parties independently arrive at the same shared secret. So let's talk about security implementations. So the DHKE provides strong security as long as the private key remains secret. An eavesdropper who intercepts the public key can't calculate the shared secret due to the difficulties of the discrete logarithm problem, as we mentioned in previous slides. If a private key is compromised, the attacker could deprive the shared secret from the key pair involved. However, previous or future communication sessions remain secure if they use different key pairs. So just because you get eavesdropped one time, as long as you're using different pairs, you want to be eavesdropped again. So a property um, known as the perfect forward um, secrecy is that it is crucial to remember that the strength of the DHKE relies on the proper generation, exchange, and disposal of the keys. Okay, perfect. Let's get into some quiz problems. So, which of the following best describes the principle behind the Diffie-Hellman key exchange? So, is it both parties generate the same public and private key pair and exchanges their keys? Each party generates a unique public private key pair, exchange their public keys and then their own private keys to generate a secret key. Is it both parties generate a shared secret without exchanging any keys? Or is it D, each party generates a unique public private key pair, exchanges their private keys, and use their own public key to generate a shared secret? So the answer is for this one will be, let me get here, it will actually be B. So the principle behind the DHKE involves each party generating a unique public private key pair. They then exchange public keys and use their own private keys, and then the other party's public keys to independently compute the same secret. So I know B and D sounds very familiar, but please just keep in mind of the last part. This may be a way of how I ask a certain quiz question. So just keep in mind of that the differences that we have here. So make sure that we follow these public and private. We have to understand that um, the private key is to be generated to generate a shared secret, and that the public keys are exchanged, not the private. Ooh. All right, another quiz question. So, what mathematical problem is the security of the DHKE based on? Is it the integral factorization problem, discrete logarithm problem, the ecliptic curve problem, or is it the quadratic reduced problem? So the answer for this one is B. So as we discussed before, this is going to be the logarithm problem that we use for the DHKE. Okay. Okay. Perfect. And then let's get into this. So in the context of the DHKE, which of the following statements about the security implementation is true? So is it A, compromise of a public key breaks the security of the DHKE? Is it B, DHKE on its own provides verification of the identities of the communicating partners. C. Compromise of a public key breaks the security of the DHKE. Or D. Is an eavesdropper can easily compute the shared secret if they intercept the public key. So the answer for this one is, let me get a pen, C. So if a public key is compromised, the compromise in DHKE, the shared secret could be calculated, thus breaking the security. DHKE does not provide the identity verification on its own. It doesn't confirm that you're communicating with another party that you think you are. As such, um, it is vulnerable to it is valuable to the man in the middle attacks unless combined with additional authorization methods. Also, due to the difficulties of the discrete logarithm problems, even if an eavesdropper intercepts the public key, they can't feasibly compute the shared secret. Okay, let's go on to the next problem. I think this is our last quiz problem. Um, I wish we have one more. So, which form of the arithmetic plays in a crucial role in the Diffie-Hellman key exchange? Is it A, the factorial? Is it the factorial arithmetic? Is it the exponential arithmetic, modular arithmetic, or the linear arithmetic? This one should be a very easy one. As we talked about it numerous times in the past, and this is actually the modular arithmetic. Perfect. Last quiz question here. So, in the context of the Diffie-Hellman key exchange, what are the main use of the shared secret deprived by the two communicating partners? Is it A, it is used as a public key in sequential communication? B, it is used as a private key in subsequent communication? Is it used for symmetric exchange encryption of an actual message data? Is it used to verify the identity of the communicating parties? And the answer for this one is C. So the main use of the shared secret deprives from the DHKE is that the symmetric encryption of a actual message data. Once both parties have computed the same shared secret, they can use it as a key in a symmetric encryption algorithm for secure communication. It is important to note that the DHKE does not provide authentication of parties. It only provides a mechanism to deprive a shared secret key securely. Oh, let me go on to the next. Okay, cool. So that actually ends our lecture for this week. What's going to happen next week is that we're going to continue this conversation of uh, of the basic key exchange, but we're going to go into a little more depth of different methods that they have. So if you have any questions or concerns, please feel free to reach out. Thank you. Take care, everybody.